We're going to work a problem involving Bernoulli's principle. Part of the solution of the problem will require us to use the volume flow rate conservation equation that you would have encountered if you read that section of the lecture notes. We have a pipe that is tapered, wider at one end, more narrow at the other end. At the left end of the pipe, at a location we'll label as 1.1 is here. The speed of the water is 3 meters per second. The center of the left end of this pipe is 2.60 meters above the ground. The cross-sectional area of the left end of the pipe, the area of that circular cross-section is 0.40 square meters. One of the unknowns in this problem that we will seek is the pressure at that location, P1. That will be the first of two unknowns that we will be looking for. At the other end of the pipe, the center of the pipe is a height H2 is 0.90 meters above the ground. The water that's flowing in this pipe has a density of 1,000 kilograms per cubic meter. That's the constant density of water, unchanging density. At the right end, the pressure in the fluid, the water at that point in the pipe, 60,000 Pascal. It's flowing outward at a speed V2. The speed of the fluid at that location is V2. Now, we don't specify that the end of this tube is open to the air. Unless you're otherwise told that it's open to the air, then you will assume that the pipe continues onward for a certain distance that we don't care about. The height of the center of the pipe, I've already mentioned, is 0.90 meters above the ground. The pressure there, P2 in the fluid, 60,000 Pascal. The cross-sectional area is 0.10 square meters, and there is the second of the two unknowns that we seek. We want to know the speed of the fluid at that point. Well, we'll first find the speed of the fluid, and we will use the volume flow rate equation, which I will do here. A1 times V1 equals A2 times V2. A1 is 0.40, drop the units. V1 is 3. Right hand side, A2, 0.10. And there's your unknown speed, V2. V2 then is 12 meters per second. That's the first of the two unknowns we're looking for. We'll need this value when we work or finish the problem by using Bernoulli's equation to put this value of V2 up there. And what will remain in the Bernoulli's equation is just one unknown, P1. All right, let's do the substitution. P1 still unknown. Rho is 1,000. Half of that is 500. And V1 is 3. It gets squared. Now we have rho, which is 1,000, times 9.8 makes 9,800. times H1, which is 2.6. That equals P2, which is 60,000. Drop the units. Plus 1/2 of 1,000 is 500 times V2, which has already been determined as 12. It gets squared. And then you have plus 9,800 times H2, which is 0.90, drop the units. That one equation has just one unknown, P1. I'll solve now for P1. $840. Final result, 110,840 Pascal. And this completes the solution to this Bernoulli's equation problem. I hope it will be helpful to you in your studies. See you next time.